Today we are talking about solutions. So far in this unit, we've talked about gases and gas laws. Last time we talked about solids and how they can be crystalline or amorphous. And today we're talking about liquids and solutions. So a solution is a homogeneous mixture, meaning you can't tell the different parts from one another. They don't have to be liquids, but they usually are. So a solution contains two parts: the solute, which is what's getting dissolved. So that's what seems to disappear or take on the state of the solvent. The solvent is the substance that does the dissolving. So this thing doesn't really appear to change states. When both the solute and the solvent have the same state, the solvent is the component present in the largest amount. So here's an example. I have salt as my solute, and I have water as a solvent. So when the solute is dissolved in the solvent and they're mixed, then we have salt water as a solution. So what's a solution? A solution in which the solvent is water are called aqueous solutions, which we've talked about for a while now. Water is often called the universal solvent. Solutions that contain metal solutes and solvents are called alloys. So when it's just a metal and I have different metals that are combined, that's called an alloy. An alloy is just a mix of different metals. Aqueous solutions we're a little more familiar with. It's just some type of liquid that's mainly water, mixed water. There's three types of solutions based on the solvent. So I can have a gas and a gas. For example, I'd have air. I could have a solvent as a liquid and a solute as a solid. An example of that would be mixing Kool-Aid into water. So it's still a liquid form. Then I could have a liquid and a liquid mixed together, like a lot of alcohols. Then I could have a liquid and a gas, and so the solvent's still liquid. So an example would be soda. There's a lot of CO2 in sodas. And lastly, I have a solid and a solid mixed together. That's just going to form some type of metal alloy. When one substance dissolves easily into another, it's said to be soluble in that solvent. So salt is soluble in water, oil is soluble in gasoline. Those can be dissolved in each of those. There's usually a limit to the solubility of one substance to another. So I can't just keep adding and adding and adding and expect it to dissolve. It hits a point where it won't dissolve anymore. When one substance does not dissolve into another, the two substances are said to be insoluble in one another. For example, oil is insoluble in water. They will not mix. More specifically, when two liquids are soluble in one another, they're said to be miscible. When they're not soluble in each other, they're said to be immiscible. So why do water and alcohol mix well in another? Water has a slight charge due to its chemical polar covalent bonds. Alcohol has a slight charge due to its chemical polar covalent bonds. These slight charges attract each other and they form a physical bond. This particular physical bond between water and alcohol is a hydrogen bond. So if you look at the dotted line over there to the right, the line between H and O, that's forming a physical bond, a hydrogen bond between the alcohol molecule on the left and the water molecule on the right. These two liquids dissolve well in one another and are miscible in one another. These two liquids are immiscible. So if you see oil on the top and water on the bottom, they're not going to mix together and form bonds with each other. They're just going to kind of layer on top of each other. Water has a slight charge, but oil doesn't. That's one of the reasons why they won't mix. Not all of the water molecules have their charges shown. So on my picture, they're not all showing the charges. Molecules that are similar in structure, so having charge, not having charge, tend to form solutions. This is where we get the saying that like dissolves like. It's a good way to remember that concept. The solubility of the solute in the solvent depends on the temperature. Solubility is the measured amount of solute that can be dissolved in a given amount of solvent. A solution that contains very little solute in a given solvent is called unsaturated or dilute. So if you just kind of remember that those two go together, it will help you out. A solution that contains the max amount of solute is called saturated, or it's really concentrated. And a solution that contains more than the maximum amount is going to be called supersaturated. So here's an example of what that looks like. If I have some type of red mixture, I can keep adding water to it to dilute it down and the color gets a lot lighter, or I can make it super concentrated like on the right. Honey and these little crystal rock candy are examples of something that's really super saturated. Solids increase their solubility in water as temperature increases. So more sugar can be dissolved in water at higher temperatures. If you think about this in the lab, if you're boiling water, the sugar is going to dissolve way faster. This is how candy is made. We can make it super saturated by adding lots and lots of sugar at high temperatures. All candy is a supersaturated solution of water and sugar. So let's estimate the amount of KClO3, which is this kind of pinkish orange line to the right, that can be dissolved in 200 grams of H2O at 70 degrees Celsius. So if you look at this chart on the y-axis, it says solubility, grams solute in 100 grams of water. The bottom is temperature. So if we're looking at 70 degrees, we just need to go up to where it says 30. So at, let me just read my points here and I'll talk about it. So interpolating from the graph, if we observe KClO3 at 70 degrees Celsius, it appears that 30 grams of KClO3 can be dissolved in 100 grams of water at 70 degrees Celsius. So if we're asking about 200 grams of water, we would be able to dissolve 60 grams of KClO3. We would just multiply it by 2. Gases decrease their solubility in water as temperatures increase. For example, cold soda or cold drinks are bubbly, warm soda is flat. As the temperature of a solution increases, so does the added kinetic energy to the gas molecules trapped in a solution. Therefore, the gas molecules move faster, and the intermolecular forces, or those physical bonds that formed within the solvent, are starting to break. More of the gas molecules escape. The solution phase and transition phase turn into the gas phase. So an example of this is fish need oxygen to breathe. Oxygen dissolves in water and fish extract the oxygen using their gills. Based on the graph to the right, what would happen to the amount of oxygen present in a lake if a factory releases warm water into the lake? So oxygen is that green line. If your temperature of the water increases, the amount of oxygen in the water is going to decrease. So probably a lot of fish would die because the water changed temperature, which means they wouldn't have enough oxygen anymore. Okay, so if you want to pause this video and take a quick break, you can. We're going to go ahead and dive into solutions part 2. So there is something called Henry's law. If you increase the pressure applied to a gas, more of the gas will dissolve into the liquid to which it's being applied. So I have this equation, S equals KH times P. S is the solubility of the gas in any unit. So it can be moles per liter, grams per liter, or anything else that's similar. The KH is called Henry's law constant, and each gas has its own constant. P is for pressure, and it's being applied to the gas over a liquid. So let's do a practice problem. Nitrogen is soluble in blood and can cause intoxication at sufficient concentrations. For this reason, Navy divers using compressed air are not allowed to go between 100 or below 125 feet. If the solubility of nitrogen gas is 1.75 times 10 to the negative fifth grams per milliliter of blood at 0.78 atm of nitrogen, what's the solubility of nitrogen in blood at 3.75 atm of nitrogen and the pressure at this depth? Assume that the temperature remains constant at 25 degrees Celsius. So we're going to use this equation. Right away, we know the solubility of nitrogen gas is 1.75 times 10 to the negative 5, and we also know pressure. So the first thing we need to do is solve for KH. So I'm going to plug in my numbers. I have 1.75 times 10 to the negative fifth equals KH times 0.78. So you're going to solve for KH. I went ahead and did that, and I got 2.24 times 10 to the negative fifth. Now, the question's asking for solubility of nitrogen at 3.75 grams. So now I know my gas constant, KH, of nitrogen, and I know the pressure. So I can use that same formula again, plug in KH that I just solved for, plug in pressure, which was 3.75, and solve for S. So when I did that, looks something like this. I'm just going to multiply those together. And I got 8.41 times 10 to the negative fifth grams per milliliter. So this says, more pressure means more nitrogen in your blood, which causes intoxication. When divers come up to the surface, if they do it too quickly, the gas expands rapidly, causing the bend, a painful phenomenon where bubbles in the blood super expand and cause blood boiling. So if you've ever done any type of diving, which I haven't, but I've read a little bit about it and watched videos about it, you have to come up at a certain speed so that this doesn't happen to you because of the pressure. Okay, so how we measure concentration. I'm gonna put all this out here. I believe you have this chart, or you're supposed to copy this chart into your notes. This is just examples of how we do some different measurements for concentration. Keep this handy with you. This would be a good thing to write on a note card for a test. Okay, let's do another example. How would you prepare 145 grams of an aqueous solution that is 2.5% by mass potassium iodide? What does it mean to have 2.5% mass solution? It means that 2.5% of the total mass of the solution is potassium iodine. The rest of it is just water. I only know that because the question literally told us that it's an aqueous solution, which just means it's mixed with water. Okay, so 0.25 or 2.5%, if you're going to get rid of the percentage, it's just 0.025. I just moved my decimal 2 places to the left. And what I'm going to do is multiply my percentage by the total mass of the solution. So I have 0.025 times 145. That means I need 3.625 grams of potassium iodide. Okay, again, I need to figure out how much water this has. So if I know the total is 145, and that's for water and potassium iodine, I just found the mass of potassium iodine. So if I just subtract those two, I can get the mass of water, which is 141.375 grams of water. So if I mix those two together, 3.625 grams of potassium iodide and 141.375 grams of water, I would get the 2.5% solution that the question is asking about. Okay, a solution of vinegar is 0.763 molar in acetic acid, which there's your equation for that. The density of the solution is 1.004 grams per milliliter. What's the molarity of acetic acid? So just FYI, the capital M means molarity. Molarity is moles of a solution over total liters of a solution. So it would look something like that. The first thing we need to do is convert liters of the total solution into kilograms of acetic acid. The reason we need to do this is molarity is equal to moles of solute over kilograms of solvent. And that's just in your chart that I showed you a second ago. So moles of solute over kilograms of solvent. We can use the density of the solution to calculate how many kilograms of solution we have. So 1 liter of vinegar is just 1,000 milliliters. That's just your general conversion for that. And then I know my density. Density is grams per milliliter. It looks a little bit like this. So if I'm multiplying those two together, I would get 1,004 grams of vinegar solution, which if I'm converting that to kilograms, it's just 1.004. So all I did was use my density to figure out grams of vinegar, or kilograms of vinegar. So we need to subtract the kilograms of acetic acid from this to calculate the kilograms of water that we have. We can use the molar mass of acetic acid to convert moles into kilograms. So generally we convert moles to grams. We're going to do that and just add a step to convert to kilograms. So the molar mass of acetic acid is about 60 grams per mole. 0.763 moles of acetic acid, which was given in the question, times 60 grams, which is your molar mass, gives me 45.78 grams of acetic acid. If I divide that by 1,000, it converts to kilograms. So I have 0.04578 kilograms of acetic acid. Okay, so kilograms of water is going to be 1.004 kilograms of vinegar minus 0.04578 kilograms of acetic acid, and that gives me 0.9582 kilograms of water. So now I have my equation, molarity equals moles of acetic acid over kilograms of water. So I can go back, plug in my numbers to get my final answer. I have 0.763 moles of acetic acid divided by my kilograms of water gives me 0.796 molar. All right, parts per million or thousand. Parts per thousand, parts per million, or in some cases, parts per billion is a frequently used method of expressing very dilute concentrations of contaminants in soil and water. Water companies, sewer companies, environmental firms, the EPA, all use this method of expressing concentration. These measurements represent the number of units of mass of a contaminant per thousand, parts per million or billion of the total mass. Usually in chemistry, we're simply converting these measurements from one thing to another. So let's do an example. In October 2001, the U.S. Environmental Protection Agency established a new max level for arsenic in public water supply. The new standard is 10 parts per billion. Convert it into parts per million. So 10 parts per billion represents 10 parts of arsenic, and then you have, I believe that's 1 billion parts total. If we were to make the bottom of the fraction 1 million, we're simply dividing it by 1,000. So we would do the same thing to the top, to the numerator, and we would get 0.01 parts arsenic and 1 million parts total. So for these types of questions, you're just converting from one thing to another, so like parts per billion to parts per million. So that equals 0.01 parts per million. A shortcut for this is to convert between parts per billion and per million. You just divide by 1,000. To convert between parts per million and parts per billion, we multiply by 1,000. If we're going from per million to per thousand, divide by 1,000. If you're going from per thousand to per million, multiply by 1,000. So all of these are just units of 1,000. Okay, next we have dilutions. A dilution is a common lab procedure where distilled water is added to a measured amount of concentrated solution in order to dilute it to a desired concentration. This can be valuable as chemicals are purchased in their concentrated form, and large amounts of solution can be prepared by simply adding distilled water, which is what I do anytime you have a lab. I have to dilute down whatever chemical it is and add water to it so that we can use it. This is a more cost-effective thing than purchasing the diluted solution, where one is essentially purchasing water. So here's kind of an example of that. I have a high concentration at this lower volume of whatever chemical that is. I can add water and it becomes a lower concentration of whatever chemical that is. The dilution formula is C1 times V1 equals C2 times V2. C is concentration, V is volume. So concentration and volumes can be any units as long as they're the same on both sides. How do we use the dilution formula? C1 represents the concentration of the solution we want to dilute. V1 represents the amount of concentrated solution we want to obtain. C2 represents the concentration of the new diluted solution after dilution. V2 represents the amount of new diluted solution we want to prepare. So let's practice this. If I have 150 milliliters of 18 molar solution of sulfuric acid are used to make 1.5 liters of a new solution, what's the molarity of the new diluted solution? So we're going to use this formula. We need to know C1, V1, C2, and V2. We're solving for C2. So all I really need to do is plug in numbers. C1 is going to be your first concentration, which is given to you. It's 18 molar. Volume 1 is also given to you. I would convert that to liters. So 150 milliliters is going to be 0.15 liters. I don't know C2. Volume 2 that we need is 1.5. So when I plug in all my numbers, it looks something like this. I just need to solve for X, and you should get 1.8 molar is your new concentration. Okay, so there's 2 guided practices today since we technically did 2 lectures. Part 1, I want you to work on first. If you don't complete that one, it's homework. If you do complete it in class or in a timely manner, then you can go ahead and start on part 2.